You just got it? Okay, good. So,
On your behalf.
okay. That's good. So then they must have forwarded it. Yeah. I'd say at least see if you're able to register. If you're not, contact me and let me see what I can do for you to compete. Okay. And it's this
Saturday, yeah.
So instead of our regular mock competition, we'll do this qualifying competition. Okay.
If you guys don't get to sign up, there's like a 90% chance that it's going to be basically, there's going to be a link that's open to everybody. If that's the case, I'll send it through Discord. So you can just check on that. So even if you don't sign up, you can still compete.
Like you have to show up there, it's virtual.
What was that?
Like is it virtual or like you have
It'll be
It's
virtual.
all virtual anyways. Yeah, the whole qualifier is virtual. Okay? So keep your Saturday free for this. Yeah? All right, so today we're gonna talk about we're gonna talk about something called rank and select. Let's start first with this big picture that's kind of useful. We all know about unsorted arrays and sorted arrays to store a set of items. And for each of those, there are very different time complexities for your basic operations of search, insert, and delete. In an unsorted array, if you want to search, you have to essentially go through the whole array in the worst case. Whereas with a sorted array, you can do binary search and speed this up. So your search is either n or log n, but in the unsorted array, you can insert quickly because you don't care where it goes. So the insert operation is fast. However, in a sorted array, insert operations are expensive because you have to move things and make space for them. Okay. Delete operations are expensive in both for the same reason that you have to make sure that the array is properly formulated at the end of the delete operation. Then you have things called linked lists, which you guys have looked at back in your data structures class, and it has its time complexities. Again, it depends on how it's formulated, but even here, you could have an unsorted versus a sorted list, and again, insert can be fast, but then most of these operations are very expensive. The delete operation can be fast if you know which item it is and if you don't have to search for it. But otherwise, you cannot speed up search in a sorted linked list because you can't do binary search. There is no such concept of getting to the middle of the list. Okay. And then there are these search trees. You guys are familiar with something called binary search trees, and a binary search tree has this nice property that small items are to the left and large items are to the right. If you have something like that, it turns out that search, insert, and delete can be performed in time big O of h, where h is the height of the tree. Unfortunately, the height of a binary search tree can be as bad as big O of n, depending on in what order you insert things. So if you insert things in sorted order, the tree would simply become very imbalanced, and the height could be very, very large. So everything, all the operations depend on the height of the tree, and this dictates the time complexities for the three operations. So that leads us to something called balanced binary search trees, where you can guarantee the height of the trees, and with these balanced binary search trees, you can guarantee that the height is always at most log n or 2 log n, and you can guarantee that all the operations, the insert, search, and delete, can be done in log n time. So this is roughly, how a lot of the data structures get designed. You look at what you want to store, you look at what operations you want to perform, and then see how to speed things up. Okay. Now, just a quick slide about something called balanced binary search trees. Well, before I do that, what I want to talk to you about is that in general, the search, insert, and delete are your basic operations, but often that's not enough. There are other operations that we want to perform. So here's an example of something called a red-black tree. The red-black tree is a great example of this balanced binary search tree implementation. And in a red-black tree, you can guarantee that the height of the tree is never going to be more than 2 times log n. And the reason that happens is because red-black trees have essentially 3 simple properties. Every node in this tree is colored either red or black. Yeah? And the root of the tree is always black in color, and you will never find a red node that's a parent of a red child. Okay, so if you take any path from the root to a leaf, you will never encounter 2 red nodes in succession. All right, and then the most important property of a red-black tree is that regardless of which path you take from the root to a leaf, the number of black nodes that you will encounter is exactly the same. Okay. In this case, it doesn't matter which path you take, every path you will encounter 3 black nodes, as long as you go from the root to some leaf. Okay? So, because the number of black nodes is exactly the same, and because you never have 2 red nodes in succession on any of these paths, you can be sure that no path will have more than 5 nodes on its path. Yeah.
From those 3 properties, what stops us from just making one long chain of just black nodes?
Because then even the failed paths, you have to make sure that the number of black nodes is the same.
I see. Okay.
And so, it has here even the failed paths. If you stop here, you'll still encounter 3 black nodes.
I see. Mm-hmm.
Okay. You can stop here, here, doesn't matter. As long as you stop at it doesn't even have to be a leaf. As long as you can't go anymore, if there is a null pointer that says there is nothing more down here, that means you've reached the end of your search. You would have encountered 3 black nodes by that time. Whereas that's not true for a simple path. Okay. Is that cool? Yeah. All right. So these are the properties, and it turns out that red-black trees, there are nice ways to insert and delete and make sure that it remains a red-black tree. And there are also some nice animations if you want to go and understand these better. There are some great animations for you to work with so that you can understand them well. But you can insert, delete, and search in this red-black tree in time big O of log n, because the height of the tree is log n. Okay? Are you with me so far? All good? Okay. So now we are ready to look at some additional problems where we want to say, given that we now have this nice data structure that allows us to insert, delete, and search in log n time, what other operations can I perform with this? That's the question we're trying to ask. And that brings us to some simple queries, such as the following. I have this red-black tree. Now I'm going to ask you the question, how many items in this tree are between 6 and 14? Okay. Now there is a simple way to answer this question. You can essentially go and visit every node in the tree, and if it is between 6 and 14, you count, and at the end you report the answer. What's wrong with the solution?
The time complexity is endless.
The time complexity is as big as the tree. If the tree has n nodes, you're going to have to visit every node, and so therefore it's going to take you big O of n time, right? What you'd like to do is to spend time that is proportional to the height of the tree, not every node in the tree. And it all depends on the query. If the query it gives you a small range, then it can be done more efficiently. If the query is the entire range, you have to go and visit every node in the tree. And here we are assuming that you're allowed to pre-process this and do whatever you want with it. But when I ask you a query, I want you to give me answers quickly. And I'm going to ask you a lot of such queries. Fine? So this is a query-based system where you are allowed to pre-process the data in whatever way you want, in such a way that you answer range queries quickly. Now it turns out that if I put in a lot of work at the start as pre-processing, I could answer these queries really, really quickly if I could take every possible range and write down the answer and compute the answer beforehand. But the problem is that something like that becomes too expensive. Okay, it becomes too expensive because there are too many possible ranges. And even if you're a little bit smart about it, the number of such possible ranges can be as bad as big O of n squared. And so what happens is that computing these ranges and figuring out the numbers, pre-computing them is just too expensive and it's not worth it. So what we're going to do is to do some partial computations so that our queries can be answered as quickly and as efficiently as possible. And remember, our queries are always going to look like that. I'm going to give you two numbers, A and B, and I'm going to ask you, tell me how many numbers are between A and B. It might be 6 and 14, or it might be 3 and 7, or it might be 9 and 16, or it could be anything. But for every possible query, your job is to give me that answer as quickly as possible. All right? So the trick here is in storing some extra information in the tree so that you're able to do this as quickly as possible. And it turns out, I won't go through the whole exercise for you, but I'm going to tell you that the trick here is to store some special information in each of the nodes of the tree. All right? And that special information is something called the size. It's actually the size of the subtree. So at every node, I am going to store the size of the subtree that's rooted at that node. Which, if you go through this process, you'll see that these are the numbers you end up with. If you look at a leaf, it's the root of a subtree that has only one node in it. So this is going to be all ones. This guy here is the root of this subtree, which has 3 nodes, and therefore the number 3. This guy has 4. That one there has 9 nodes in its subtree. Right? This one here has 7 nodes in its subtree. And the root of the tree simply tells you what is the size of this whole tree. So I'm not storing answers to the kinds of queries that are going to come up. Instead, I'm going to store just the size information, and you'll see that this can actually help me tremendously. The reason it helps me tremendously is because when I ask you these range queries, when I ask you how many items are between 6 and 14, or between, let's say 15, sorry, let's say I want to ask you between 13 and 38. What will happen is that if I want to ask you how many items are between 13 and 38, you'll see that, sorry, let's say I want to ask you between 12 and 38. What you'll see is that this entire subtree here falls in that range. This entire subtree here falls in that range. So without having to actually go through the nodes in that subtree, I can add things up and give you answers pretty quickly. And in fact, the answer for the range 12 through 38 is going to be 4 plus 5, 9 plus 1, 10, and the answer is going to be 10. So I'm devising shortcuts so that I don't have to go through subtrees and inspect them fully, and yet get answers for how many items are going to fall between A and B. Okay, so as I said, if my question is between 12 and 38, I can very quickly give you that answer just by looking at this guy's size here and this guy's size here and adding 1 to it for the root of the tree. Okay, questions? All right, so it turns out using this size information is quite dramatic, and it can answer these range queries really, really efficiently. Now, the example I gave you was a little bit simple, but even for complicated examples, it turns out that there are nice ways to compute the right answer. Okay. So in the end, because of this trick of storing the size information at each node, the size of the subtree, it turns out that I can do something called rank and select in log n time. Now, what is rank and select? A rank operation asks you for the rank of an item in a sorted list. So if I go back to this example here, the rank of item 12 is going to be 1 more than the number of items that are smaller than this. In this case, 2, 5, 6, 10, and 11 are smaller than 12. So that is 5 items are smaller than 12, so therefore the rank of 12 is 6. Because if I put it in sorted order, 12 would sit in the 6th position, right? So rank is simply its position in the sorted list. Rank problems are actually quite interesting because you're saying, tell me what the rank of 12 is. And you would sort of go through this list and figure this out. Now, if I'm not very careful, in order to find the rank of 12, what I have to do is I'd have to go to every node, figure out how many of these items are smaller than 12, and then add 1 to that sum, and that would be my answer. But then, if I ask you for rank of 45, you would have to go through the whole tree. So that would become a big O of n time operation, too expensive. So that's why it turns out that the size information can become very powerful for you and can give you that answer very, very quickly. In fact, we can show that you can compute the size in log n time, okay, or big O of log n. So that's what the power is of this method, where instead of just storing the data value in each node, we add this extra augmented information of storing the size of the subtree rooted at that node. So with that information, we are able to answer rank. The select operation is another operation that can be performed fairly efficiently using this one. The select operation is the exact opposite of the rank operation. In select operation, I will give you a rank. I'll say, give me the 12th smallest item in this list. Now, 12th smallest item doesn't mean it's number 12. It just says if I were to take all the items here, put them in sorted order, I want to know what value sits in the 12th position. Of course, I can go through this entire array and put them in sorted order and then pick out the 12th item, but that's too expensive. So question is, how do I do this without having to look at everything in the list in the worst case? And so again, it turns out that there are nice ways to do this. If I want the 12th smallest item in this list, I look at the root of the tree, I see that on the left subtree there are 9 items, right? So therefore the rank of the root of the tree is what?
10.
It's 10. So if you want the 12th item, it's going to be on the right side. Okay? So I can just bypass all of this because I just don't even have to look at it. And now all I'm left with is to say, find me the second smallest item in this subtree because everything else has been taken care of. If I want the second smallest item, again I start here and it says that there are 5 items in the left subtree, so therefore the second smallest item must be somewhere there. So I restart my search from here and I still want to find the second smallest item. And here it tells me that the left subtree has 1 item, so therefore the root of this subtree has rank what?
2.
It has rank 2, so therefore the second smallest item is 30. So the 12th smallest item in this tree is number 30. Okay, so with just some simple calculations, I was able to figure out that the 12th smallest item in this humongous tree is number 30. Did that make sense? So this is called the select operation. The rank operation is exactly the opposite, where it says, if I give you number 30, your job is to figure out what is its rank. So if you essentially reverse all the things that I just told you, you can figure this out. Okay? So rank and select operations can be very efficiently computed as long as you store the size information in each of the nodes. And remember, the size is the size of the subtree. Okay? Now, this turns out to be a very powerful tool for doing lots of other interesting things. So we're going to move on to try and do something even harder next. Fine? Any questions so far before I go on to the next question? Is this going too fast? Do you want me to slow down, explain anything again, or you're all okay with this? Should I explain anything again? All good? Okay, good. So the next problem is something called the k-frequent values problem. Sorry, it's not k-frequent values, it's just frequent values. K is the number of the problem. And you can go to this link here if you want to know more about this problem. I'll tell you a little bit about the problem. So the problem is as follows. Again, you're given a list of items. All right? You're allowed to pre-process this as much as you want. And you're told that some of the values are repeated. Okay? And then you're going to be asked the question, you'll be again given a range, and you'll be asked the question, tell me the most frequent value in this range. So just like before, I'm going to say your range is 6 to 14. And your job is to look through the location 6 through 14 and figure out which item is the most frequent in that portion of the array, or that portion of the sorted list. Okay? And once again, just like before, we're going to make sure that we store some extra information. And in this case, the extra information is not only the value stored, not only is it the size of the subtree, but we're also going to store the frequency of each of the numbers that are present. Okay? So remember, you're told that some of these guys, there are multiple copies of them. So if I store the frequencies, this is what I get. So I'm told that there are 7 copies of number 13, 2 copies of 12, 11 copies of number 10, and so on and so forth. Fine? So that's the list that you've been given. And now I'm going to ask you things like, I'll give you a range, 6 through 14, and your job is to tell me what's the most frequent item in that range. Okay. Again, you don't want to go to every node, figure out whether it's in the range, and then look at these frequency values and report the best one. That's not what you want to do, because that becomes too expensive. Instead, we want to pre-process this information to a limited extent so that we can answer these queries as quickly as possible. Is that clear? So, what do I do? How can I go from for a certain range and answer these queries? Well, it turns out we've now done several things, right? We have the actual value, that's the actual numbers that are present in our list. We have the number of copies of each one of these, right? And then we also have the size of the subtree, like before. We're going to need that as well if we want to do this efficiently. And then we're going to need one more piece of information at each node. We're going to have to figure out at each node what is the most frequent item in the subtree here. Okay. So for instance, in this case, the most frequent item is 15 itself. If you look at this subtree here, the most frequent item is 15, which appears 14 times. If you look over here, the most frequent item is 10 because it appears 11 times. So at each node, I could store how many items, what's the most frequent item, or at least the frequency of the most frequent item, right? And if I store that, then it turns out that I could do some things quite efficiently. So I store the size, I store the frequency values, and I store the largest frequency value. Okay. So now let's ask the question: if I simply asked you what is the frequency of 15, well, that's easy because I'll just find 15 wherever it is in the tree, and then I know I've stored over there the frequency of that item, and so I can simply read it out. Easy question. But what if I asked you what is the most frequent item between 10 and 16? Remember, I don't want to go and look at 10, 11, 12, 13, and 15 and figure out their frequencies and then find the largest. Instead, I want to do some subtrees in order to do this. Yeah.
When you say 10 to 16, you mean the actual
Yeah,
index position?
I mean here the actual values, not the
Values, okay.
positions. If you ask for positions, it is a little bit harder.
Okay.
Right. So here we're just asking between 10 and 16 in terms of the values, which is the most frequent one. Now, over here, if we have that extra information, then we could figure this out because we can this is similar to the other work that we did with the rank and the select, and you have to essentially do a traversal that's very similar to it. We'll know that 10 to 16 it's not there on this side of the tree, so you can essentially ignore that part. So from 20, you're going to come down here, and you know that 10 to 16 is all over here, and so I only need to confine myself to the search. Then you will realize that 10 to 16 spans this guy, so there's part of it on this side of the tree and part of it on this side of the tree, and so you have to work on both sides. You have to figure out which is the most frequent on this side and the most frequent on this side and report it. You can't just read out the most frequent item that's stored here, because here there are some things that shouldn't be part of that tree. There are also some things here that shouldn't be part of your consideration. So you can't just give the answer based on whatever is stored here. So instead you have to go and dig a little bit deeper. So you know that 10 is on this side and 16 is on this side, so for 10 you come down here, and then when you get down to, you finally reach 10, you realize that you don't have to look at the left subtree because that's outside the range. The right subtree is empty, so I don't have to do any work there. So all I need is the is the frequency of 10. And so currently, the best answer I have is that the most frequent item I've seen so far is only 10. Then I can check the frequency of 11 and compare it and figure that out. Then on the right side, I'm going to do a little bit more work. I'm going to come down here and realize that everything in the left subtree is in the range. So I can simply report the most frequent item here and keep track of it. I can go on the right side, and the right side I don't have to look at anything because all items there are bigger. And so that leaves me with just 15, this subtree, and this subtree, and then this node here. And you find the largest of the most frequent item of the ones that you looked there and report. And it turns out that there is a nice way to write this in a recursive manner if you're comfortable writing recursive code. Otherwise, it's you're going to have to struggle with this a little bit.
So I guess the main idea is like you initially start at the root and you have some range.
Correct.
If you're partially covering the range, you have to look at both sides.
Correct. That's a critical point.
That's
yes.
one case.
Yeah.
But if it covers the entire range, then we can take that value.
If it covers that entire range, then you can take that value and accumulate it.
Yeah,
with
accumulate
whatever
it.
it's done so far.
That makes sense. How do we know this is, because sometimes we have to split.
Right.
How do we know we're not looking at the entire tree?
Right. So you may have to store additional information at each node.
Mm-hmm.
You may have to store the smallest value and the largest value in the subtree rooted at each node. If you have that, then essentially that question would get answered.
Okay.
Right?
Mm-hmm.
Because over here, I would store the information that goes from 2 to 45.
Mm-hmm.
Over here, I would go 2 to 18, and so on and so forth. And so you would be able to answer that question. And I have a picture here that tells you that. I've taken a simpler example here. Right, so I have 7 items, and I believe these are my frequencies, right? Is it? Must be, yeah. And you can see here that I've done it a little differently here. Is it? Sorry? Yeah, I've done this a little differently, so it's a little confusing here.
Looks like the numbers are the values, so 1 appears 21 times?
1 appears 21 times, 2 appears 9 times. That one is fine, but the tree I have here is not a binary search tree. It's a segment tree.
Yeah.
So why did I choose that? That's what I'm trying to figure out for myself. You can still think of it as a binary search tree where you have 4 over there, and then things divide this way. But then this is actually kind of confusing. So this is a slightly different way of organizing the data. This is not using your binary search tree. Instead, every node has what's called as a segment. So it's called a segment tree. The root has the entire range, going from the smallest to the largest. Then you take that entire range 1 through 7, and you break it into 2 pieces. On this side you have 1 to 4, and that side you have 5 to 7. Okay? And then 1 to 4 again gets broken down into 1 to 2 and 3 to 4. And then at the end you have the leaves which correspond to your items. So it's a slightly different organization. This is called a segment tree. And at the bottom here, I have the information about frequency. Okay? So this says 1 appears 21 times, 2 appears 9 times, and so on and so forth. Now, what do I have at the next level? Well, I've taken the largest items, the frequency, the higher frequency, and I've sent it, I'm storing that information at the next level. So here 21 is the larger of 21 and 9, 6 is the larger of 6 and 3, 14 is the larger of 14 and 11, and 7 is larger of these two here. And then again at the next level, you have the larger number being sent up, and then all the way at the root, you have the largest of the numbers, okay? So this is a slightly different way of organizing your ranges, but it essentially captures the same information. Fine? Now, so you're going to need this organization if you want to deal with positions. But if you don't care about positions, then this works out. Then the previous organization would have worked out just fine. Right. So if I have the entire range to work with, then I can just read it off the top of the tree and say number 1 appears 21 times, and that's your most frequent item. So if there are any of the ranges that are already marked here, then it's simple. Then I just read it off whatever I have. However, not all ranges are going to have this nice property. If you want to go from 3 to 6, then it's going to need parts from different parts of the tree. And you'll see that 3 to 6 is, it has parts in the left subtree as well as the right subtree. So 3 to 6 will get broken up into 3 to 4 and then 5 to 6. And then you will do the computations for 3 to 4 separately and 5 to 6 separately, find the most frequent item, and then figure it out at the end. Fine? So in 3 to 4, this one will say go to the right, and then here you have your answer. This says there's an item number 4 that appears 6 times, and that's the information you're going to pass up the tree. And then on this side, from 5 to 6, again, you'll be done over here. It says something appears 14 times, in this case it's 5, and then between 14 and 6, 14 is larger, so you're going to report 14 as the answer, not 21, not something else. Is that clear? So you have to kind of work your way down to the right level of the tree, and sometimes you may need several nodes of the tree in order to make this answer. I'll show you a slightly different picture that will help you understand this a little bit better. Okay. In general, what you'll see is that
We do have markers here.
oh, yeah.
Those are only bad.
Doesn't work.
Yeah.
So in general, you have a tree that looks like this. You're going to start at the root, and you're going to either go left or right, and so on. If you're given a range A to B, your job is to first find A in this tree. And remember, everything is a leaf in the tree, so it's going to go down the tree somewhere, and this is where A is going to be. And you need to also search B, and B may not be over on the right, it may be somewhere over here, so let's say it goes down here. Okay, so let me use a different color so that this makes sense. So here's A, here is B, and the place where A and B were on different sides of the tree happened over here. Okay, so everything above it and on the other side, I can just ignore all of that because I don't care. It's outside my range and will not be part of my answer. And over here, I am going to come down this tree, and anything that hangs off as a right child, and all the subtrees that hang off over here, they're all going to contribute some answers, and they all need to be considered. And similar considerations will happen for the other side, anything that's on the, that hangs as a left subtree is going to contribute to the answer in completeness, and so you can use all of those. If there are any right subtrees here, or if there are any left subtrees on this side, I can ignore them because they're going to be outside my range. Okay, so it turns out that as I walk down my tree, I will either include things that I walk down, that I encounter along the way, or I will include things that are entire subtrees that I don't have to go and traverse. And so in the end, the amount of work that I perform is proportional to the height of the tree, and so everything is still big O of log n. And that's where everything works out, and you get finding the maximum in a given range, or the maximum frequency in a given range can be done in this nice manner. I think my next slide has to do with positions, so this could be a little more complicated. Right, so here I've changed the problem so that you're actually looking at array positions, and you're asking what is the most frequent item in the array position. So we are assuming that our items are in sorted order. Okay, the only problem is that some of the items may get repeated. So I have 2 1s, 4 3s, 1 6, 3 9s, a 15. 3 24s and a 29. Fine. So this is my array, and these are my locations. So this is location 1, 2, 3, all the way up to 15. And now I am going to give you a range of positions, not range of values. And I'm going to ask you what is the most frequent item here. Okay. So if I go from 2 all the way to 12, then the most frequent item is 3 because it appears 4 times, right? But if I go from 5 to 12, then 3 only appears twice, and now the most frequent item is 9 because it appeared 3 times, right? So it all depends on where I start, where I end. It might be in the middle of a string of repeats, and so it gets a little messier now. It's basically a modification of what we did before, but you have to work a little bit harder. All right. Again, like before, we're going to break down the ranges into smaller pieces. So you have your ranges here, and then we are going to build our tree, but this time I think I'm building the tree using positions, not using values. Okay, so this is with positions 1 and 2. This is with positions 3 and 4. Here it's 7 and 7. Here it's 8 and 10, and so on. Why am I doing it this way? No, it looks like I'm still doing it with values. So sorry. So here I have 1 and 2 as the children. Here I have 3 and 4. Here I have there are no 5 and 6s. Yeah, there are no 5s, and there is a 6. So there's a 6, and then there's also the next one is a 9. Then you have 15, 24, and 39. So you can see that each of the values are here. 1 appears 2 times, 3 appears 4 times, 6 appears only once, 9 appears 3 times. So those are your leads of the tree. And now I build the next level by simply combining things and keeping track of the most frequent item in each of those pieces. And so you have all that information stored appropriately. But now the search is a little bit harder because you're dealing with positions as well. Okay? So you have to keep track of some extra information as you work through this tree. We can look at a specific example and make sure that we understand this. let's say that, so let's say we want to go from 5 through 12, right? If you go from 5 through 12, we know that the most frequent item is not 3, but it is 9. And so we need to make sure that this works out right. So if I want to go through from 5 through 12, essentially I have to locate 5 in this tree, I have to locate 12 in this tree, and then look at everything in between and report the most frequent item. Okay? Now if I want to look at position 5, I know it's to the left of this, I know it's to the left of this, I know it's somewhere here. Right? If it is somewhere here, we know that the only item here is a 3, but this position 3 started in location 3 and went all the way to 6. And so if it is 5, I will only get a frequency of 2 for 3. And that's what I'm going to pass up the tree. And when I send that 2 to up the tree, I will only keep track of the 2. And then over here, I am going to keep track of, this entire subtree is already part of my location. So I only need to know that 9 appears 3 times. 9 appears 3 times, 3 appears 2 times, so therefore 9 is a better answer. That's what gets passed on up there to the tree. So even though you've stored something else, the stored values are only useful if you're taking that entire subtree. Otherwise, you have to recalculate it as and when needed. Okay? And so from that subtree, you get 9 appearing 3 times. But then you go to the other side, and you will come down here, and you'll see that only one thing has to become, well, you're going to have to look at this as well as this, and you'll see that here 15 appears 1 time, and 12 will tell you that 24 also appears only 1 time, not 3 times. So both of these will give you something that appears once, something that appears once, and then you'll report that 9 appears 3 times, and that's the most frequent item. Are you with me so far? Yeah? It is a little more complicated than before. The challenge here is to try and write recursive code for it. Do we have time to write something like that? Yeah. Right, so here there are 2 challenges. One is to build the tree and store all the information. The second is to do the search in the tree, right? What are all the pieces of information that we are going to store? So should we try and do a simpler version than this or the most general version?
Maybe the simpler version is better.
Simpler version looks much better, right?
Yeah.
The other one looks way more complicated. Yeah. Let's try to do this. So here we would ask the question, given the lower end and the upper end of a range, which items within this range have the highest frequency, right? So in this case, I would ask between 3 and 6, which item has the highest frequency? And between 3 and 6, we know the answer should be 5, but the question is how do we arrive at this? So when we ask the question, we're going to ask the question about, so the query would be 3, 6. This query would start at the root of the tree. We know we are looking at 3, 6, and by knowing where that split occurred, the left subtree goes from 1 through 4, the right subtree goes from 5 to 7. This shows that I have to do the search on both sides. So in fact, for a part of this range, I'm going to look at the left subtree, and for part of this range, I'm going to look at the right subtree. So I will end up with two queries. One is a query from 3 to 4, because we know that the left subtree only ends at 4. And on the other side, I'm going to have, it goes from 5 to 7, so I only have to go from 5 to 6. So essentially, I'm breaking down this range 3 to 6 into two sub-ranges. One I search in the left subtree, and one I search in the right subtree. Okay? And this you can figure out based on the information that's stored at the top of the tree. Then, when if I'm looking for query 3 to 4, starting from here, it tells me that that entire range is in the right subtree. And so I will go to the right subtree there and read off the answer, and I would have the answer 6, which then gets passed up the tree, which then gets passed up the tree, and for now the answer from this side is going to be 6. Okay? On the second recursive call, this guy also will, you will figure out over there that if you go to the left subtree, you'll find this range 5, 6 in its entirety, and all you have to do is to read out the answer. And there it tells you that the right frequency is 14. 14 gets passed up the tree, and then you get two answers from the two recursive calls, and you take the larger of the two. So the answer at this point would become 14. And it would tell you that it's item 5 that has frequency 14. Is that clear? So in order to implement this, you would have two parameters for the query, A and B. You would start at the root of the tree. If the entire range lies in one of the subtrees, either the left subtree or the right subtree, then you just have to make one recursive call and restart with the left child or the right child. If it happens to span both the left subtree and the right subtree, then you have to set up two recursive calls, one for a smaller range on the left subtree and one for a smaller range on the right subtree. Then once you get that, you have to essentially repeat this with a recursive call, so it'll go through that same process every time. And so ultimately it will have an answer, and it'll come back up the tree, and the recursive call will get processed at the end. And every time you get two different answers, you just pick the larger of the two values. So if you're comfortable with recursion, this can be handled reasonably easily. Okay. My recommendation is for you to go and try this out. Obviously, it won't happen this weekend because I'm hoping that you will all be busy with the qualifier competition. But we can go through with this in one of our future sessions, and maybe Rick, you can, if you have a session with these students on the mock competitions, then you could talk about this perhaps. Any questions about what we've done here?
I have a question, but after this.
Okay. Let me see if I don't have any more slides. There are lots of variants of this problem that turn out to be similar. It's a similar approach where you decide what information you're going to store in each node in the tree, and then process it. The one thing we didn't talk about was how to build this tree from bottom up. And there, it's worthwhile to see that if you take the array and first start with the array, then you can essentially take two nodes at a time and start to build bottom up this whole tree. So these two guys come here, these two guys come here, these two guys come here, and this comes here, and you need to put in dummy nodes as needed. And then you build the next level of the tree, which combines two at a time, and then you combine two at a time until you have the whole tree built. You can do this whole building of the tree in a recursive manner, and as you go up the tree, you can pass the largest one and keep track of whatever is needed. So building this tree can also be done in a recursive manner, and just as the search happens in a recursive manner. So it's worthwhile for you to try out how you would do this recursive tree building and then recursive tree searching.
So what if there is one more number
Yeah.
with the same frequency? Like consider 8 having a frequency
Fine,
of 14
yeah.
or 7.
Yeah, if there are two values, if you get the same answer from the left subtree and the right subtree, then you have to make a decision on which one you pick. And it doesn't really matter because both answers are correct. But the rules of the problem may tell you something. It may tell you that you want the smallest number with the highest frequency. In that case, you should always take from the left subtree instead of the right subtree.
Okay. Is there any provision like we can store these two values as an array? Like there are more than one frequency, then it could be stored as an array.
You will never need to do that because you can always recompute it from the child node. So you never have to store more than one thing. If you catch yourself storing more than one thing, then you should rethink what you're doing. There may be an easier way where you only store one of the values. Okay. In a lot of these problems, so even here, for instance, if you recall, if you recall here, each of these is frequencies. It's possible that these two numbers are the same. In that case, you have to decide what you want to store over there. 11 is the right answer, but it doesn't matter which one you pick. Yeah, you said you had a different question.
So I was actually doing a problem that I put in the Saturday contest that I couldn't get, and it's a little more general.
Yeah.
It's like a data structure question where you have some intervals.
Yeah.
You have some left and right endpoints for each interval.
Yeah.
And you want to do queries where you want to give an interval query.
Yeah.
And find the maximum.
Meaning how many intervals cross that point?
Each interval in the data structure has a value,
Right.
like 7. It doesn't actually mean anything for the actual interval. It can just be
a number.
A number, yeah.
Yeah.
You want to query an interval, and any interval that touches even at one point, you want to see the maximum.
But are these intervals disjoint?
They are disjoint.
They are disjoint.
Yeah, they can be like from here all the way here.
So here we call it frequency, but it could be your number.
Yeah, but at like let's say at the root, we always had one entire interval. In this, at the root, we can have like 1 through 7, a giant space, 10 to 100. Does this change the problem at all?
Oh, you mean it's a collection of disjoint pieces of intervals?
Yeah.
Well, that doesn't, even here, there are these big gaps because 18 to 20 is a gap, 20 to 28 is a gap. So I'm not sure I follow your problem completely.
So
let's start again.
Mhm.
So you're given intervals as the input, but those intervals are all disjoint.
they may overlap, they may be disjoint. They're just some intervals.
Okay, so then they're not disjoint.
Yeah. Okay. Yeah.
Okay, so they're not necessarily disjoint, but your values are associated with these intervals
Yeah.
or with subintervals?
With those intervals
With
themselves.
those intervals. So every interval has a weight or some
weight.
some number.
Mhm.
And you're saying, so your picture looks something like this. You've got a collection of intervals,
Mhm.
right?
Mhm.
And each one has a number.
Yeah. Oh wait.
Oh wait, so 7, 6, 14, 5, and so on, right? Something
Yeah.
like this. And now what do you want to do?
Now there's two operations. The first one is you query a range, and
Yeah, you're asking for a range. Okay.
any interval that touches that range, I want to find the maximum. So in this case, I should
So
report 10
even though you
or
don't have
11.
the entire 10, you're
Yeah.
still going to count 10.
Mhm.
Okay.
Or in this case, I will report 11 because that's the largest one. In
Oh,
there.
11, sorry, yeah.
Yeah.
Okay.
So that's the first query. The second one is I want to insert.
Yeah. Yeah. All right. Yes. So, so here's the way to approach it.
Mm-hmm.
Firstly, you have to decide how you're processing your intervals. So your intervals look like this. Things like this. What you do is, so there are some minor concerns with regard to endpoints. Let's assume for now that all the endpoints are disjoint. So every endpoint, I am going to put it down.
Mm-hmm.
Each point here corresponds to either a left endpoint or a right endpoint. Now, I am going to store not those intervals, but I'm going to store these intervals.
Mm-hmm.
Okay, so now I will store that as one, this is another, this is another, this is another, this is another, and so on. So those are going to be my nodes in the tree, and their values are the highest interval that spans that region. And because there are no endpoints, nothing ends in the middle, it's basically all the intervals that span here, and I'm going to just take the largest one. Okay, so for instance, if each of these has a value, so let's say this is 9, 7, 6, 4, and 11, my scores are going to be 9 for this, because that's the largest. It's still going to be 9 over here, because 9 is larger. It's still going to be 9 over here, because 9 is larger. Then it's going to be 6. Then it's going to be 6. Sorry, then it's going to be 7, because 7 is larger. After that, it's still 7. And then I think there's another 7, and then there's 11, and then there's 11. So each time you keep track of. So you're going to have this tree, and you're going to store the largest in that node, as well as in the subtree.
This
Alright?
looks very similar to line sweep. Am I just making that up in my head, or?
Well, this is what it's going to look like after at any given time. Now your question is, how do I insert it?
Yeah.
So that's the more interesting question.
Mhm.
So let's look at that. If I'm going to insert something, what's it going to look like? It's going to look like, let's say, from here to here. Okay, let's say. So now I have 2 new endpoints, and I have to do something about it. So this endpoint comes somewhere there. Let me use a different color. Okay, I have this endpoint to insert, and I have this endpoint to insert. Now, oh, but I would end up going and fixing everything, so that doesn't help me.
Yeah.
Yeah, so, yeah, so that's fine, that's fine. Right, yeah, so I need to change my solution a little bit. So I would still do a segment tree like what I have here.
Mhm.
So this would be the entire range, and then that gets split into 2 sub-ranges and so on and so forth. And then, yeah, so I never if I have to insert something, oh yeah, so at each node, I am going to simply say, right, so each node has a range, a left and a right, and it's going to keep track of the heaviest interval, but is it in one place or is it the entire range? Yeah, it's going to keep track of some heaviest range that it has seen in this region, but that won't help me because it may not span my. Right, okay. So I will keep track of the max anywhere in this region.
Okay.
Okay. So anywhere in this range, if there is there is some place where there is the heaviest interval, that's what I'm going to store that. I'm going to store that information here.
Mm-hmm.
Now think of what I'm going to do. I'm going to. So I have to do two things. One is search and one is insert. If I want to do a search, if this entire node is part of my search, all I have to do is to read out this number. I only need to know that, and I will pass it up the tree. But if only a part of it is there, then I'm going to walk down the tree and come to the right place where I don't need to go down any further.
Mm-hmm.
So the search is easy, right? So all I'm left with is inserting.
Mm-hmm.
So if the inserting goes, let's say the insertion goes from this node to this node,
Mm-hmm.
because each of these is an interval, and this is anything below here is all included in this. So we're assuming that it starts. This is the left end point, and over here this is the right end point. So I'm only concerned about all these four nodes, and so I only have to change the maximum values in these four things if it gets affected. So I will check over here. The new interval goes from the left end point of this to the right end point of this. So it includes this entire subtree. If it's larger than the maximum I've stored here, I'll update it. I won't do anything below this.
Here's the part I'm not seeing. This is before we were sorting by sort of just one point. In this case, there's a left endpoint and a right endpoint.
Yeah.
So how do we always guarantee that the searching is possible by both at the same time?
So we typically do it separately.
Okay.
First search the left endpoint and the right endpoint separately. The left endpoint involves coming down the tree to some leaf.
Mm-hmm.
Right?
Mm-hmm.
And then I'm going to walk my way along that same path. So let me redraw this picture here. If this is the root of the tree, my left end point is somewhere there, my right end point is somewhere there. Imagine that I'm going down all the way to the leaf, because the way we've done the intervals, the endpoints are at the leaf of it. Okay?
Maybe I said my question wrong, but let's say I have an interval that has a really small left endpoint, but the right endpoint is the largest right endpoint.
Doesn't matter. Ultimately, all I have is A and B. And A is somewhere in the tree and B is somewhere in the tree. If B is your right endpoint, way right, doesn't matter, because I'm going to add two extra sentinel values, negative infinity and positive infinity. So they're always there.
Okay.
So I'm going to locate my A and my B. in the tree. And then all I have to do is to walk up this tree on both sides and figure out. And each one may involve looking at subtrees, which I only have to deal with in its entirety. I won't change anything else. So this is for the, now when you asked me, were you asking me for search or for insert?
For search.
Search. So if it is search, I only have to kind of look at these subtrees, and if any of these is whichever is the largest, that's what I'm going to pass as the true. So that part is clear, right? Insert. I am going to store at each node I'm going to store the largest, heaviest value I've seen, but I never have to go into the subtrees. I mean, that's what I have to make sure of. So I'm going to traverse this path, and at each time I'm going to see if I need to update the values that are stored there. That's all.
Okay.
So imagine that at each node, I only keep track of the largest one, the heaviest interval that spans the, so should I say it spans the whole interval or only part of that interval? That's the only thing that we have to decide.
And are we splitting by the medium? So this tree is balanced?
Yeah.
Okay.
But if you do inserts and deletes, you have all these rotations to worry about, so that makes life even more complicated. So yeah, I'd have to think about this more.
Okay.
But yeah, it looks like a good problem. If you send me a link, at least I'll know.
I'll send you the link to the problem.
The details more clearly.
Maybe we can go over next week.
Sure. Yeah, we will. Thank you, guys.
Thank you, Professor.
Thank you.